So before we start, just some updates. Next Wednesday there'll be the dental lecture at the same time at 10 in the morning. On Thursday there'll be a special seminar. Chagit today will send out a message today, an email today about that. That'll be at 10 on Thursday next week, not tomorrow.
By the same speaker.
By the same speaker as the dental. Okay, so it'll be presumably a different topic. And tomorrow is there anything? There's the regular.
Tomorrow there's one of the exceptional lectures that is called.
Okay, so there'll be an extraordinary lecture tomorrow afternoon. Okay, so that's the announcements, and now I'd like to introduce our speaker, who's Professor Yossef Hatzor. He's the Dr. Salmon Edna Professor of Rock Mechanics at the Department of Geological and Environmental Sciences at Ben Gurion University. Yossi did his bachelor's and master's here at Hebrew University. He then went to do a PhD at Berkeley, and he's an expert in rock mechanics. He's also the founding president of the Israel Rock Mechanics Association, and he's going to tell you today about a project that he has going, or had going in China. So Yossi, I'll hand over the platform to you.
Okay, so hi. So thank you very much, Chagit and Simon, for inviting me to give this talk. It's always I'm always very excited to be here. I can give talks all over the world when I come here. For some reason, actually I know the reason, I'm very excited to see my professors and teachers here. Always gives me a very special feeling. So I thank you for inviting me. And I'm going to share with you some results from the project I've been doing over the past several years in China. I do this project with this person, Xiaoting Feng, who is he was the president of the International Society of Rock Mechanics for 4 years, and he's the president of the Chinese Rock Mechanics and Rock Engineering Association, so it's very big in China. And he offered me to become a visiting professor of the Chinese Academy of Sciences. It's a screening procedure that they do, and I agreed that it was successful. So for 5 years, I've been coming and going back and forth twice, 3 times a year to fulfill my obligation in this partnership, and now it's over, and I'm fully back in Israel. The other collaborators are invited. I believe he gave a speech here a few weeks ago. He was then a master's student, and he did some contributions that were very essential for us to proceed in this kind of work which I will present. And a postdoc of mine from China who did 3 years with me under the program of the China-India Vatat postdoc fellowship, a competitive fellowship. He did 3 years of very good work, and now he's back in China. So the outline, there will be no delta O16, O18, no chemistry. The talk is strictly structural geology and rock engineering. It's very applied. And I apologize for my voice because I caught a cold last week in a conference that was in Maya Hamisha, and I apologize for this. So we're going to talk about a phenomenon called Rockburst. It's a dynamic release of energy during tunneling. It is a big hazard because the stored elastic energy in the rock is being released spontaneously once the excavation is being made. And that energy, that released energy, can be transferred into kinetic energy of ejectiles that fly out of the rock mass. They can be several meters wide. They can stop the excavation process. And if, for example, we're talking about a tunnel that is driven 2,500 meters below ground with a tunnel-boring machine, and all of a sudden there is a huge block that is released from the periphery of the tunnel, it's becoming a major engineering problem because there are those TBM machines don't know how to drive back, so they can only go forward. So that's a major problem. More important than that, people die. It's a big risk. People die, and it's a major concern of the Chinese that are exploring deeper and deeper excavation ventures in China to deal with this. The first ones to recognize this were in South Africa, in the deep gold mines at depths of 2,000, 3,000 meters. So the South Africans started the literature on this. Professor David Cook, Professor Cook, many important, and then Professor Ferrats from Minnesota continued, and they set up the foundations for this rock-based issue. Now the Chinese are facing with this problem, and they're trying to understand it in their own way. And I had the luck to come from a country where the deepest tunnel is about 300, 400 meters max. And to be able to get involved in a project like this and to contribute my modest part to the project. So I will give you one example, but they have more of these problems in other places. So this is this, so the lecture is until 10:45? Yes. So the project that I will show you is called the Jinping Hydropower Project. It's in the Sichuan province. What it is, it's very interesting. This is the Yangtze River. It's one of the largest rivers in the world. I think it's the second largest river in the world. It drains the Himalaya. And along its path, there is a place where it makes a bend, where it makes this bend. So the difference in altitude from here to here for the riverbed is 250 meters. So they said that already Chairman Mao envisioned this. I don't know if it's true or not, but they have thought about this already from the 70s. How about if we make a dam here? So a 300 meters dam, of course everything they do has to be the biggest in the world. So the 300 meters dam, back then was the biggest in the world. Okay, so we do a dam, a 300 meters high dam here. There's a V-shaped valley, so there's going to be a big reservoir here. And here, drop the water in vertical shafts to circulate the turbines. Each will make 600 megawatts, so you can manage do the multiplication by yourself. And then the remaining water, after the water does the work, goes back to the riverbed and continues to flow. Now, so here we're making 600 megawatts times 6. By virtue of the energy from dropping the water 250 meters. Then the water continues to circulate along the riverbed, so we didn't alter the ecosystem for the green opposition that hardly exists there. And then once we get here, as I said, the difference in elevation is 250 meters. So what they do, now they drill 4 tunnels through the mountain that is 2,500 meters high above the level of the tunnel, 2,500 meters high. So the tunnels they don't need a big inclination just for gravitational flow of the water. So here again we have a 250 meters elevation difference. So now again they drop the water here in 4 vertical shafts that branch out to 8 high pressure tubes that rotate 8 turbines, each one 600 megawatt capacity. To give you an appreciation, the pump storage plant in the Gurion is 1 turbine of 200 megawatts only. So we're generating here in this scheme about 3/4 of the energy consumption of the state of Israel without burning any coal. So it's completely green. We're just using the water and gravity. And in this particular region, because it's so deserted, there's also no need to evacuate anybody because nobody lives there. So it remains just an engineering challenge to build a dam, to drill the tunnels, to drill the shaft without too much damage. So here's the Jinping 1, the dam, 305 meters high, while it's being constructed. When I was there, this was 2011. And certainly an engineering challenge. The dam is butting against those rocks. The rocks are metamorphic limestones, marbles, not very easy rock for engineering, very discontinuous, not so strong. And the thrust of the reservoir is sent through the dam to the abutments, and the abutments need to provide the support for the dam. So that's a challenge. And this is the left side of the project. And then you see on the right side, after the tunnels, we have this room, this chamber, the main powerhouse. These are its dimensions. It's 70 meters high, it's very high. And in here, they put the turbines, which they built by themselves. In the beginning, in the first hydropower projects, they bought the turbines from Siemens, from Germany, and then quickly they learned how to do it by themselves. Generally, a good word of advice. I, a long time ago, stopped looking down at the Chinese. If you just do the statistics, if you have a population of 1.3 billion people, and you admit less than 1% of the top universities, you can imagine that you're getting very smart people there to do the engineering and science. So they did their own turbine here, and then the 8 turbines do the electricity, then they transform a house and send the water back to the river. The geology is very complex. It's a folded rock mass. And it discontinuous, as I said, because there's bedding planes and joints. You can see there's bedding planes, and there are cross joints, there are folds, and there are shears, and there are faults. And the tunnel goes from Jinping 1 to Jinping 2 under this thick overburden of rocks. To show you the view, this is the kind of topography, V-shaped valleys, very deep canyons. So that's actually a problem because the valley is there is some relaxation of the stresses in the rock, and those areas are actually relaxed. And we want, when we enter a rock mass to do a tunnel, an underground opening, we want the rock to be as stressed as possible to mobilize as maximum shear as we can along the joints. So, number one, you have this relaxation due to the topography. Number two, the orientation of the stresses are changing now. We don't have vertical stresses and horizontal stresses that we would like, but because this becomes a free plane, then the principal stress becomes inclined. And now we have to deal with principal stresses that are not horizontal as vertical as we would like. So these are the type of challenges that poses. The stress regime, you know better than I, it's the tectonics of Asia, Eastern Asia, high compression in this area, very high compression, and there are different models to try to study numerically the stress distributions. This is like having a model, we can do this. If you're not assuming tectonic stresses, the horizontal stress distribution, if you're not assuming tectonic stresses, this is if you do assume tectonic stresses, and that's with other tectonic stresses, this band here delineates the area where the stress direction alters because of the topography and becomes inclined. So what we're showing here is that the principal stress changes. Here sigma 1 is horizontal, then sigma 1 is vertical, and then sigma 1 is horizontal again. So when you're driving a tunnel through this kind of rock mass, you're driving a tunnel through stress regime that keeps changing. And what they have encountered during the tunneling are episodes of energy release in the form of Rockburst. And you can see those events documented while they were tunneling. So the group I'm working with, which is located in Wuhan, it's in central China in a province called Hubei, they were following the project and monitoring its advance with various multitude methods, geophysical and other, to start to obtain as much information as we can from the project. And Of course, while they were doing this, they also recorded the Rockburst events, and you can see them here along the axis of the tunnel, several Rockburst events. And you can see them here within the tunnel. You can see different events documented, different dates. In one of those events, 7 miners died. And in one of those events, the TPM had to stop. So it's a major problem. So this is the dam on the left. These are the 4 tunnels. These are 2 access tunnels, drainage tunnels. And as I said, these 4 tunnels here are split. Each pressure tunnel here splits to 2 tubes that bring the water to 8 turbines down here. So the problems we're talking about are in the center region, where those high stresses are being released due to the excavation. In order to study this, we had to employ a numerical approach, and there's no way you can do this analytically. And the numerical approach we adopted was an approach called discontinuous deformation analysis. It's a numerical method that was invented by this person, Dr. Gurion. Gurion is actually a mathematician that during the Cultural Revolution was sent to work in work camps underground. And I told this story here, so some of you maybe remember, they put him to work underground, and since he's a mathematician working on topology, he saw the traces of the joints cutting the sides of the tunnel, and he worked out an analytical solution for the removability of 3-dimensional blocks that intersect in the roof.
He came out of this.
Yes, and then the miners noticed that wherever Gurion was having his lunch, nobody was down. Everything was set. So he published it after he finished working on the ground. He published it in the Chinese mathematical journal. My professor, Professor Goodman from Berkeley, is not a mathematician. Goodman actually is also a geologist like me. They did his civil engineering, PhD in civil engineering in Berkeley. And so he doesn't have the mathematical tools to develop such an elegant method, but he saw this journal in Chile, in this paper in Chile. So when Gurion was invited as a visiting scholar to Berkeley to the math department, they made a connection, and the switch sides went to the engineering side and became a worker for Goodman. Several years after that, I came for my PhD, and we shared the office there at Berkeley in the same department, and we became very good friends. So I didn't do my PhD on DDA. It was too advanced for me. I did it on block theory, that method that he developed in the mines. But then he needed to obtain a PhD. He didn't have a PhD. So he developed DDA and submitted that as his PhD. By then he was already 50. So that's his PhD. For this, he's the sole author. Block theory, this method I told you about, is the authors of Goodman and Sheen. DDA is his invention. It's actually a new numerical method that did not exist before, which allows to model discontinuous system, block systems. And it solves rigorously the displacements of every block in the mesh, and the strains and the stresses and so on and so forth. So it has advantages over other existing methods. It has limitations, of course. I will not I promised there will be no modeling. So if you're interested, we just came up with a book on DDA. The ISRM, the International Society for Rock Mechanics, has commissions, and I'm chairing professional commissions, and I'm chairing the DDA commission. So together with my co-chair, Ma Due from Australia, and Yossef, of course, we submitted as our product of our commission this book within the ISRM book series. So it really goes through all the background of the theory, the equations, and everything. It's not mathematical, but it's very honest. It comes out from first principles of physics and mechanics, and very nicely implemented in American. So these 2 chapters bring the theory, and then those chapters is my responsibility, how to input geological parameters to the code. Because a lab engineer uses this code, you don't know what you get. So it's very important what you put in. So this is this chapter. Then the verification, also very important. So I had a series of PhD students working on the verification of DDA. And then applications, underground rock slopes. And then Again, she contributed a new chapter, is a new contact theory. I'll tell you a small episode. You all know Bonin Biran, some of you know Bonin Biran, I go to Biran, now she's at the Geological Survey. So she was my PhD student trying to do three-dimensional DDA, it didn't work. And for 2 years it didn't work, and she was ready to, I don't know what, she was really desperate. Again, I liked her very much. And he knew she was very sincere and very strong. And we tried to do dynamic vibration of movements in 3 dimensions, and it didn't converge at a certain point when we added the blocks. Gano realized that he had a problem with his contact algorithm, and he sat back and wrote the whole contact theory again. It took him 5 or 6 years, but it was prompted by Bonin's failure to succeed with his 3-dimensional DDA. Of course, I had to give her other things to work on so that she can get a PhD thesis. She was very scared. She was very depressed, frustrated. So, but it worked out for the better. So then, DDA, as it was published, it was insufficient for us. We needed to enhance it a little bit. One enhancement I did with a postdoc that came to work with me, Bao Huirum. He came from Singapore, and that is implementation of non-reflective boundaries. So when the energy is being transmitted, the DDA, in the original DDA, there was no method to absorb this energy. So if you think about modeling a blast underground and you want to model it correctly, if you don't have these boundaries, you need to model the whole mountain, and that's impossible to do with mirroring blocks. So with these non-reflective boundaries, we can actually concentrate near the blast and study the deformations near the blast, and then these boundaries will make sure that we don't have reflections that are artificial, that will obscure the numerical computation. The other enhancement was done by Yuval Tal, who, because we wanted to simulate the excavation sequence, we wanted first the stresses to equilibrate, and then remove the tunnel, just the way it's done on the ground. But then we also needed very accurate stress distributions in the mesh. So in DDA, the blocks are what we call simply deformable. They all undergo the same deformation, and there is a more advanced version with a finite elements mesh superimposed on the DDA mesh, which is called the manifold method. So Yuval first did it with manifold, and then did it in DDA, implemented an ability for us to remove elements while the computation is going on. So to give you an example here, for this block here, see, because there is this discretization of the DDA blocks, we have a very accurate solution. So if you consider this block here in the roof, once we remove the tunnel, this is what happens. The center, the lowermost layer bends, and because it bends, we are developing tensile stresses here and compressive stresses here within the same block. And that is enabled because of the discretization within the block. And you see how nicely we are stabilizing this beam by developing those stresses here. This would compressive stresses. This would be the thickness of the compressive arch that transmits the compressive stresses. And these are the compressive stresses, negative in this case, and the tensile stresses here. So we were not able to do this before Yuval did this. And it was very difficult because he had to understand how the manifold method is working and then to put it in. Okay. So here's what we did. The first question was, what is the level of in situ stress on the ground? Surprisingly enough, they did not know. And they didn't know. If you are going to open an oil field, then you go down and do your own fracturing at any depth you like, and you can get the stresses within some limits of accuracy quite well. You can do flat jacks and different overcoring, different methods of in situ stress. You're probably studying your rock mechanics class. Those methods didn't work here. And they did not know what is the level of the in situ stress. Of course, they know the vertical stress. The vertical stress is the weight of the overburden. That's not a problem. Now, when we don't know anything about the horizontal stresses, what we typically normally do, we assume elastic expansion in the other two directions, and it is the result of the Poisson ratio of the rock, and assuming those boundaries are rigid, then that develops a horizontal stress. This approach is called uniaxial strain. It's very common to assume that in basins, geological basins. However, we know that we cannot do this here because it's not a uniaxial strain condition, it's in situ stress. They're very high in situ stress, and we need to obtain. So what we did, I mean, it's not us, they were interested in the deformation in the response of the rock to the tunneling. So here's what they did. They took this tunnel, this is one of the 4 headrace tunnels that I showed you, and they drilled 4 boreholes towards empty rock. And then they came in with a research tunnel, so they were able to convince the owners, who you realize that those people I work with, they are just parasites over a huge project. They are just the scientists and the engineers that are walking around there. But they were able to obtain this from them and to obtain this extra tunnel, which is a research tunnel. And then, once this research tunnel was being excavated, all these monitoring devices that they put here came into life and began to monitor things. So they put in there a televiewer to monitor the microfracture of the rock. They put in acoustic devices to measure the change in the seismic velocities of the rocks. And they installed a device that is called sliding micrometer. Not too many people know about it, but it was developed by Professor Kovari in the 70s. It's a very accurate mechanical device that provides the displacement of the rock once the rock material begins to expand. And of course, they shared all that information with us. So here's an example of the sliding micrometer data in the 4 positions in the borehole. So these are the depth. The first 3 points were cut by the excavation when it was advancing. The other, we're recording the formation. And you see the deformation of every one of those points over time. We used that deformation, those values, to constrain the level of the horizontal stress and the shear stress on a rectangular element by trial and error. What we did, we mimicked the conditions in the field with the manifold code. We kept the vertical stress constant, and we changed the horizontal stress and the shear stress on the boundaries until we found the best fit solution. Yuval did this. Yuval did this under my guidance. And first we want to check that we're able to maintain the stresses in the code. It's not very easy for numerical reasons. And this only shows you that we can impose initial stresses. Then we mimic the excavation sequence. First, we prepare the mesh with 17 measurement points from one tunnel to the other. And then we excavate in the model this tunnel, the headrace tunnel. And then we remove the same way they did in the field, the top heading. And then we remove the bench. And we compare the output of the measurement points in the numerical model with the output of the measurement points in the sliding micrometer. And we change the combination of sigma x star xy, with the horizontal stress and the shear stress, keeping the vertical stress constant, and then we find the best match. So this approach is called inversion, sort of an inversion, and this is the result. Yuval did all that, okay? So you can see the RMS, the error between what was being measured and what was being computed for different values of horizontal stress and different values of shear stress, keeping the vertical stress constant. And you see that the solution is not very sensitive to your assumption regarding the shear stress, but it's very sensitive for your assumption regarding the horizontal stress, and this is the lowest error. This is the minimum error. And this error provides this point here, which is the minimum error, the best fit between the numerical and the measured values, gives us an value, an estimate of the horizontal stress, which is about 35 MPa. It's a very high stress. And so, to show you how it works, this is just a simulation of the best fit solution with these stresses that are the best fit stresses, and you see the agreement between the manifold values, displacement values for each measurement point, and the measured values from the sliding micrometer that they installed in that borehole. And then, of course, these are normal stresses and shear stresses. We use stress transformation to find the principal stresses, and you see that indeed they are not horizontal or vertical, but inclined. This is just, it comes to show that when a country, a state supports engineering and science, you can do almost everything you want. And this is right now the situation there. I mean, if you're an engineer, scientist comes with a good idea, they will give you the means to check. So, of course, the manifold method was applied for a continuous domain. The discretization is just to improve the solution, but the medium is assumed continuous. And it was good enough for the value of stresses. But now we want to study the mechanism of Rockburst. And for this, we must introduce discontinuities to the system. And to show you that discontinuities are important in the mechanism of Rockburst, you can look at this picture here and you see that this is a buried TBM. That's a big problem for engineering. If you have, the length of the tunnels is 16 kilometers, so imagine that at the kilometer number 8, the TBM is stuck. What do you do now? Can't go back. You have to disassemble it, take it out in parts, and start over again. Big mess. So if you notice, the TBM is buried by fragments of rock that are originated from a block that was ejected from the rock mass. So actually these discontinuities control the deformation. And if you think about it, it makes sense. If you read the original papers on Rockburst by Fairhouse and Little Cook, they all talk about fracture propagation, about fracture initiation and propagation. That the high stress concentrations on the sidewalls of the tunnel prompt fracture initiation and propagation, and then the sides collapse in a spalling kind of, or buckling type of failure mode to generate fracture. So basically, they assume that Rockburst is a phenomenon associated with continuous and strong rocks. So the notion in the rock engineering community for many years was that Rockburst is a phenomenon associated with continuous and strong rocks. What we're saying here is actually changing the concept, because we're saying the following. We say that if you have discontinuities, then the shear strength of discontinuities is clearly much lower than the shear strength of the continuous rock. Therefore, given the stress concentrations and the existence of pre-existing discontinuities, existing blocks will be ejected along discontinuities much before the intact rock will begin to fracture. That makes sense. The only thing you need, the only precondition is that those blocks are removable. That's a kinematical problem, and that's the issue that remember I told you about, we resolved a long time ago, how we distinguish between removable and non-removable blocks. And to support this assumption, this hypothesis, this is a compilation of many events of rockbursts in China, documented the number of events versus the kind of rock material. And you can see that the majority of the rock bursts occur in a rock mass that is defined as blocky. Blocky is a definition of rock mass that was coined by Terzaghi. I don't know how many of you are familiar with the name Terzaghi. Terzaghi is the founder of soil mechanics, originally a geologist, studied engineering, and he invented soil mechanics. Terzaghi invented the concept of effective stress and the theory of consolidation. And you cannot build buildings and you cannot design piles without a theories of exactness that are still active today. He is so revered that my professor Berkeley, he describes Terzaghi's theories. Terzaghi was never wrong. So interestingly, Terzaghi was also interested in geology, and before he immigrated, escaped to America, I think he went to Harvard, if I'm not mistaken. He was there in Austria, and he went to the tunnels and mapped them and came out with a classification. It's called Terzaghi's rock load classification, predicting what would be the expected rock load that needs to be supported given the kind of rock mass. And he classified rock masses into different categories. One of the categories is blocky rock. Blocky rock is a rock comprised of blocks. And you see that the majority of rock bursts do occur in blocky rock mass as we predicted. Now, to give you an idea what kind of energies we're talking about, consider this simple block here. Everybody can see it's removable. We don't need block theory for this. So the block is, if it's not removable, there's not going to be any block ejection because it's simply unremovable. But if it's removable, like we made it removable here. Now we impose hydrostatic stresses to make the analytical solution simple. Hydrostatic stresses on the mesh. And then we removed the tunnel. But this is done analytically here. This is an analytical solution developed by Dr. Head, my postdoc. And he came out with a peak acceleration once the block is being ejected of this number. This number is very, very high. And at first, when we saw this number, it didn't make sense. However, this number is actually correct. It's the same order of magnitude. And if we apply now DDA for the same problem, similar problem, with DDA, we can track the dynamic deformation, and we can look at the displacement, the velocity, and the acceleration. So tunnel is being removed here, and this is done with no gravity, so the block is displacing in this direction, and then this is the volume, and this is the peak acceleration. The bend was solved analytically. This time it's done numerically for a single block. And we're getting velocities, block velocities in the order of 4 meters per second. And this is what people have been reporting. Kaiser and Chai from Canada are reporting values of 3 meters per second. Outlet is very studied in a lot of Rockburst in South Africa, is reporting 10 meters per second, and so on and so forth. So this is certainly within the expected range, and this is the kind of energies we're talking about. So if we're talking about energies, let's just do this briefly. I will not trouble you, of course, with all the calculations, but we are looking for the energy change. How much the energy stored, the elastic strain energy changed because of the excavation. So we're starting with a continuous medium, and then we remove the tunnel, and we are asking how much the energy has changed, total energy has changed in the annulus outside the tunnel once we remove the tunnel. So for this, the solution for this is analytical. Ben will give this by himself, and it's a complicated solution. And the result that Bengu reached was that after 3 diameters from the tunnel center, there isn't much change in the energy. So all of the energy change is constrained between the tunnel boundary and about 3 diameters away from the tunnel center. It's about 70% increase, and 170%. And that we coined the term the affected zone. That's, for our purposes, when we want to introduce joints, it's still too large. So we studied this further, and when we looked at the strain energy density, distribution outside the tunnel. And he found that when we're looking at the strain energy density, most of the change is restricted. Most of the increase in strain energy density is between 0.5 from the tunnel face to 1.5 diameter from the tunnel center. So this is where we expect most of the rock bursts to occur. I'll tell you the secret. The reason we did this is actually so that we don't have to compute all the blocks to 3 diameters. So we look through. But you can look at the change of the strain energy density before and after. So depending if we're looking in this direction and going in this direction, you can see the increase. And you can see depending on the in situ stress ratio, 2, 1.5, and 1. So that's hydrostatic conditions. At 2, that's 1.5. You see in the roof, because the initial stress here is higher than this, so the increase is about 25 times, and then it goes down very rapidly. At 1.5, it's almost the same. And it's then the same if we're going in this direction, the values are lower, but still about 1.5, the values change about the same, strain energy ratio. So we have theoretical grounds to claim that we don't need to compute all the way to 3 diameters. It's complicated. If you think about joints with spacing of several tens of centimeters, you're ending up with huge measures. It becomes a technical problem to compute. So here's what we're saying. We're saying that the original energy plus the change in energy, 1.7 times the original energy, that is the energy change because of the tunnel. And that has to be balanced by 3 energy components. So that's your energy budget. One component will be the elastic strain energy that goes into the rock by deformation. The second energy component will be the kinetic energy of the ejected blocks. And the third energy component will be the dissipated energy by shear along the joints. So the elastic strain is very easy, because if we run DDA, we can calculate the deformation of every block and calculate the elastic strain energy. The kinetic energy, I showed you, we have the velocity, so we calculate the kinetic energy. This we don't know, but we know this analytically, so we found this by subtraction of these 2 parameters from here, and we obtain the shear, the dissipated energy that is going on shear. And here's how it looks if we're looking at this kinetic energy of the entire system. This time we took a sparse mesh, and therefore we could handle it to 3 diameters. You see the kinetic energy change once we remove the tunnel. You see of the whole block system, you see how it is affected by the friction coefficient. And with small friction coefficient, 0.25 here, the kinetic energy is very high. And this is how it goes down if we increase the friction coefficient of the joint. So the kinetic energy is a function of 2 things, primarily. One is the in situ stress value, and the other is the friction coefficient. You can see it here. This is the block that will be ejected, and you can see how it's happening in time. This is the kinetic energy of the block, how it changes as a function of the initial in situ stress with a constant coefficient of friction and stress ratio. And this is how, with a constant stress and stress ratio, how the kinetic energy of the block changes with increasing friction coefficient. So these are the elements of the problem that need to be considered. So we were able to use measurements from the field of the energy. They measured the microseismicity, and using geophysical methods, they came up with the expression for the seismic energy release during tunneling. This is an example of an event that was captured, and this is the expression for the energy that they wanted. They can calculate over a period of time, given their geophysical array system that they put in the tunnels. You see how many things they can do, and nobody tells them that there's no time and no money and so on and so forth. They can do a lot of things. And this is the direction of the tunnel. So they were able to follow the advance of the phase with this geophysical array of accelerometers and advance them with the tunnel phase and calculate the amount of energy emitted over a day or during a single event. And if we compare, this looks too good to be true, well, the fact is that it was here. The value that we got for the same conditions, the same stresses, same rock properties and so on that they were in the place where they documented, gave us about a half, but we are calculating it two-dimensional, so it's 1 meter. In that day, they advanced 2 meters, so if we multiply our result by 2, we reach the value that they monitored over the day of that major rock burst that caused the death of these 7 people. And if you look at the numbers here, they're huge, they're very, very high. So it's a lot of energy, major earthquake happening because of this rock burst. I will, a few more minutes. This is a quick study of the sensitivity to to the different components. So if we look at the friction, we see that the friction change of friction causes the kinetic energy to go down, whereas it doesn't influence so much the other two energy components. And at this time, of course, I'm only looking at the affected at the rock bursting prone zone, which is smaller, to make this calculation possible. Then the inclination, you might ask, what is the role of the joint inclination? So we studied that, and you see how it changes with the angle of the dip, how it affects the different energy. Well, we can discuss this, maybe why each of these look like that. Joint spacing is important. The joint spacing controls the block size, and you can see that there is a change in the dissipated shear energy with increase in block size. And of course, the last one is the elastic strain energy, and of course it goes down with increasing Young's modulus. This is all very intuitive, and so we want to do something useful with this, because in the end, we want to help. So the geologists have different ways to classify rock mass quality. When we want to classify students' quality, we look at your exams and we take the average of all your coursework, and this is our index of what is your quality. I don't know if it's good or bad, but it's an index. Rocks have different classification methods. Some of them are very famous, like the Q and RMR. And more recently, Professor Hook proposed the geological strength index GSI method that scales rock mass quality. So what are the parameters? So basically, the nice thing about it is that it's graphic, you can see. So he's saying if the rock is continuous with little joints, it's a good rock. And if the rock is disintegrated with very, very many blocks, it's a bad rock. And if it's schistose or it has done a lot of shear deformation, it's even worse. So one is the blocky structure. The other, you can imagine, is the condition of the joints. If the joints are clean and rough, then there's a lot of friction on the joints and it's good. And if the joints are smooth and there's thick infilling on the joints and it's bad, so it goes in this direction. If the two parameters you come from across, and you're getting the rock mass quality, the GSI index. And then this tool is very useful to, if you want to build a tunnel, based on the exploration, the boreholes. If people want to bid in Italy, in France, in Romania, in China to do your tunnel, you give them the GSI, they can know what exactly they're going to face. Are they going to face a good rock? Are they going to face a poor rock? And then they can see how much it will cost them to do the tunnel, can give you a price. So what we did is we took GSI values and put assigned values that can go into the DDA code. Like the spacing, the length, the bridges, joints. If you look at them, they're not continuous. They sometimes are interrupted with what we call a rock bridge. Those rock bridges are very important. If you look at if you know about it, there's a big slide that happened in the city Frank in Canada. One morning, the mountain collapsed and the city was covered with debris. What happened? And one of the explanations is that it was a bedding plane dipping towards the valley, but it was not discontinuous. So this is a rock bridge, and then there's creep on those segments, and then at a certain point it ruptures, the whole thing goes. You think you're safe, we're not safe. So the rock bridge, we can model those things with the bridge, the length, the spacing, the friction, all those things. So what we're doing, we are putting GSI into DDA, marrying between the two, to show you. This is a mesh of GSI of 55, this is a mesh of the GSI of 75, you can see the difference. And we study the response. So once we remove the tunnel, this is the kinetic energy of the block system in the rock bursting prone zone. You can see that Dafka, the high energy, the worst case, is not the best rock, it's the medium quality rock. It's the GSI 6570, this area, that produces the highest earthquake, if you like, or rock bursting event. That's because if the rock is very good, then the joints are widely spaced and the friction is high, and then the energy with the rock is very low. If the rock is too poor, it absorbs very low energy in the first place. So in the middle range is the worst condition, and that's quite a surprise. But we feel confident enough, we're able to publish this in the journal of the field. It's called Tunneling in Underground Space Technology. And as for the energy, we're getting this in kilojoules, 4,500 kilojoules. It becomes someone in this so about here. So the take-home message here is that if the rock mass that is prone to rock bursting is not necessarily the best rock mass, as was previously assumed, but it's the more medium quality rock mass, as I explained. And if we put this on logarithmic scale, you see that the spike here is at about 60 GSI. So this is not rocket science, this is rock engineering, and of course there's a lot of assumptions involved, but it gives us the direction. And you can also see if we find a correlation between the GSI and the Chinese classification method, as every country has its own rock mass classification method, we see that we're talking about this area of class 3 in Chinese terms, and class 3 is 2 and 3 is where most of the documented rock bursts occurred in China. So what to do? So the trick is to take out energy from the rock. So when we do the tunnel, we take out energy from the rock. But if we do a full face, we remove the face in one go, then we're getting a very high burst of energy, and then nothing happens. But this is very high. So if we can deal with this, is okay. If we cannot, then we can do top heading and bench, as I showed you before. And so in the first time, there will be this one, and then the second time, there will be this one. And if this is too high, we can first remove the third of the roof, and there will be a little spike, and then we'll get a big spike in the end. So this is already a question of design. It's what you take from the analysis, and it's less important for us, but it shows you that we can provide useful tool to design the tunneling operation in such rocks so that we can minimize the hazard associated with rock burst. Thank you very much.
About your solution, you have the TBM which naturally drills the whole section.
Yeah, not applicable. Not applicable. Not applicable for TBM.
It's not applicable.
No.
Not applicable at all.
No, not applicable for TBM.
So you have to drill the whole tunnel with another system like the classic.
But the TBM, they have another thing they do is they distress the rock by drilling ahead of the TBM, let it distress a little bit, the TBM is protected, and then they can proceed. But the top heading and bench is a methodology that cannot be used in TBM type of operation, only in the conventional. And those 4 tunnels, they did 2 with TBM and 2 with here they call it, I don't know why, every method that is not TBM, they call it NATM. Don't ask me why. Drill and blast is the correct term. So they did 2 tunnels in drill and blast and 2 tunnels with TBM to study.
5,000 G acceleration.
Amazing.
Yeah, it's pretty amazing.
It's instantaneous. Only the second it leaves the rock, then it.
So you think that's measurable to be able to measure?
Nah, it's like a rocket. It flies out. It can be measured.
Much more than a rocket.
Yeah, it's true.
5,000 G.
Yeah, but it's theoretical because what happens is it's not like a G during an earthquake that the earth continues to shake. Here, once it loses contact with the rock, it drops to 0. No force. So So it's just instantaneous, the first moment that it's been ejected.
First millisecond.
First millisecond, yeah. But the velocity falls within the range when we look at the velocity. I was also very surprised to see this. Ken?
Also on the surface, is it possible that similar mechanism can affect rockfalls? So stresses are totally different. However, if one block is getting outside and change the stress around it, so can it make a Rockburst?
You mean on the surface?
Yeah.
On the surface? You need to absorb a lot of strain energy to provide the engine for the Rockburst. So we don't see this in rocks unless you're looking at a rock slope like in Chiquitamata in South America with a slope of about 1,000 meters, and all of a sudden you decide to drill a tunnel in that 1,000 meters high slope. They are approaching that, not so high, but of course it's stepped and so on and so forth. But there could be enough stresses there that at the portal you may be getting such events at the portal. It has to be very deep. This is not a problem that is related to Israel at all.
Any more questions? Thank you.